Welcome to part 4 of my video playlist about the best methods to acylate alcohols for the preparation of carboxylic esters. This presentation is about the direct acid-catalyzed condensation of carboxylic acids with alcohols. This is one of the most relevant strategies for preparing low molecular weight esters on a large scale, but is not always applicable to structurally more complex starting materials. This reaction is always acid-catalyzed because carboxyl groups or deprotonated carboxylates are not electrophilic enough to react with alcohols. And if no stoichiometric amount of some water-absorbing reagent is used, this reaction is an equilibration, and either the resulting water must be continuously removed by distillation or a large excess of alcohol or acid must be used. As sketched here, the alcohol can add to a protonated carboxyl group or, under harsher conditions, to an acylium cation. Alcohols that readily form carbocations can also be esterified this way, but ethers or olefins are potential byproducts. The ideal catalysts for acid-catalyzed esterifications are strong, inexpensive acids that can be readily separated from the product. Gaseous hydrogen chloride and sometimes even concentrated aqueous hydrochloric acid have often been used with success. Potential byproducts are alkyl chlorides. Sulfuric acid is also often used, but during the reaction it will get diluted by the water formed. Alkyl and dialkyl sulfates are potential byproducts. These have much higher boiling points than the corresponding alcohols or alkyl chlorides, and catalysis with sulfuric acid is therefore better suited for esters that can be purified by distillation. One further problem of highly concentrated sulfuric acid is that it can oxidize sensitive starting materials. Sulfonic acids are a bit less aggressive than pure sulfuric acid and are also often used to catalyze esterifications. Again, alkyl sulfonates can be formed as byproducts and must be handled carefully because of their potential mutagenicity. A practical alternative are acidic ion exchange resins, because these can be removed from the reaction mixture by filtration. Ester-cleaving enzymes, such as lipases, can be used both for the hydrolysis and the formation of esters. Lipase of Candida antarctica can be immobilized on polymeric supports and be used to catalyze enantioselective ester formation in organic solvents. I'll show you some examples in a minute. The main advantages of acid-catalyzed esterifications, if compared to the use of stoichiometric amounts of condensing reagents, include the fact that unactivated carboxylic acids are stable, while acylating reagents can hydrolyze. Moreover, because acid-catalyzed esterifications are equilibrations, the water content of the starting materials is usually no issue. These reactions are also more environmentally friendly, because no waste other than water is generated. Then, no expensive catalysts are required. Most common catalysts are inexpensive and ion exchange resins can be recovered and recycled. What may be considered a disadvantage is the fact that either a large excess of one starting material or some strategy for the continuous removal of water will be required. Then, because water is liberated, water-sensitive catalysts cannot be used, and concentrated inorganic acids will become more dilute as the reaction proceeds. This can also cause the hydrolysis of other functional groups. A further potential problem is that often high reaction temperatures will be required to remove water azeotropically. Therefore, acid-catalyzed esterifications may not always be applicable to structurally complex starting materials. Let's now have a look at some specific examples. This here is a typical esterification with an excess of ethanol and gaseous hydrogen chloride as catalyst. In this case, a simultaneous hydrolysis of the furane and the isomerization of olefinic double bonds occurred. Unprotected amino acids are usually esterified with a large excess of methanol or ethanol and thionyl chloride or an acidic catalyst. Less straightforward is the esterification with higher boiling alcohols, as in this example, where the alcohol had a boiling point of 230 degrees Celsius. Here, the esterification was catalyzed by repeated addition of gaseous hydrogen chloride, and water was removed by a stream of nitrogen. Final isolation of the product was achieved by crystallization from acetone. Even aqueous hydrochloric acid can be used as catalyst for esterifications, as shown here. Despite the excess of water, glyoxylic acid could be esterified with ethanol, and almost 60% of the target ester was obtained. This here is an optimized procedure for the preparation of the methyl ester of phenylglycine. A slight excess of sulfuric acid was used as catalyst, and the reaction mixture was repeatedly concentrated and diluted with fresh methanol to remove water and drive the equilibrium toward the ester. In this example, only a catalytic amount of taurine sulfonic acid was used to esterify tartaric acid with benzyl alcohol. The condensation was conducted in toluene, and water was removed with the aid of a Dean-Stark trap. Amines of low basicity, for instance alpha amino acids, may sometimes also get acylated during acid-catalyzed esterifications, as in the example on this slide. Treatment of alanine with an excess of oxalic acid and butanol in the presence of 5% of sodium bisulfate gave a high yield of the amide shown here. High-yielding condensations of 3 different starting materials are actually quite rare and remarkable. This is another notable example. Here, the starting alcohol contained 5 different hydroxyl groups, an acid-sensitive glycoside and a base-sensitive trifluoroacetamide. Even so, it was possible to esterify selectively the primary hydroxyl group with valeric acid with the aid of an immobilized lipase. Despite the relatively high reaction temperature, the long reaction time and the large excess of valeric acid, no cleavage of the acetal occurred. In this example, the amino acid leucine was used as catalyst for a simple esterification. The lower the acidity of the catalyst, though, the slower will such condensations proceed. It is possible to prepare ethyl acetate just by refluxing a mixture of acetic acid and ethanol, but it takes a long time to obtain high yields. One potential problem of the present example is the addition of the acid to the alkene, but this did not occur to a large extent. Ion exchange resins are often used for the industrial preparation of esters from alcohols and acids. The authors of this example found that sodium iodide can enhance the reaction rate even further. Because the starting alcohol also contained a carboxyl group, a large excess of acetic acid was required to prevent oligomerization of the alcohol. So, what are the potential side reactions? Some acids tend to decompose when heated with strong acids. These include acids with carbocation stabilizing substituents at the alpha position, because the corresponding acylium cations fragment into a carbocation and carbon monoxide. Examples would be pivalic or citric acid. Then, acids with an electron withdrawing substituent in alpha position readily decarboxylate upon heating and may also be difficult to esterify without stoichiometric condensing reagents. Then, alcohols that readily form carbocations can also yield ethers or olefins upon heating with acids. These reactions, however, are reversible, and if an excess of carboxylic acid is used, a high conversion of the alcohol to the ester may still be achievable. As already mentioned, most acidic catalysts can also react with the alcohol and yield electrophilic alkylating reagents. This can be an issue if the target product is intended for human consumption. Some strong acids or transiently formed carbocations may also act as oxidants. If one of the starting materials is sensitive toward oxidation, some milder catalyst than for instance sulfuric acid should be chosen. Strong acids and a high concentration of starting materials can also cause the oligomerization of olefins or arenes and the isomerization of olefins. Then, electron-rich arenes, heteroarenes or alkenes may also undergo Friedel-Crafts alkylation when treated with acids and readily carbocation-forming alcohols. Here are a few more examples, but many more have been reported, mostly in patents. The recently developed immobilized lipases seem particularly promising, allowing more sensitive alcohols or acids to be esterified directly, without any dehydrating reagent. You can also find this reference list in the description of this video. The next presentation is about 2 alternative strategies for the acylation of alcohols: acylations with carbon monoxide and oxidative acylations with aldehydes. These are more of theoretical than practical interest, but who knows, maybe there are special applications where these strategies are superior to the use of carboxylic acid derivatives. See you then.